Good afternoon, everyone. Yeah, can you hear me?
Yeah.
Thank you. It's time to start the session of software mining. I'm the session chair, Yan Xiao from National University of Singapore, and my research really mainly focus on evaluating the trustworthiness of deep neural network, and we are now finding some research assistance. If you are interested, feel free to contact us. And there are totally four papers in this session. The first one. Yeah, the first one is self-attention networks for code search. The presenter is Sen Fang. Then let's start.
Thank you for watching on my talk on paper Self-Attention Networks for Code Search. My name is Sen Fang, and I'm a PhD student at Macau University of Science and Technology. I would also like to thank my co-authors, Liu Shuaitan, Tao Zhang, and Yepeng Liu for their cooperations in this project. Now I will introduce my project. Developers tend to search and reuse code snippets from a large-scale code base when they want to implement some functions that exist in previous projects, which can improve the efficiency of software development. Therefore, code search is a frequent activity in the software development. However, it is challenging to design a practical, useful code search tool. For traditional code search methods, information retrieval methods, they ignored the semantic relation between high-level description expressed by natural language and low-level source code, which undoubtedly affects the performance of the code search. Different from information retrieval technology, deep learning technology, specifically, neural networks can automatically learn feature representation and build mapping relationships between the inputs and outputs. In other words, neural network is helpful to bridge the semantic gap between the code snippet and the description. Therefore, neural code search methods outperform the IR-based code search methods and become mainstream in the code search. However, there is still room for improvement of current neural code search methods, both in effectiveness and efficiency. Dive into the Internet of RNN, we observe that the computation of the current timestamp in RNN depends on the output of the former timestamp. If the distance of two elements is much long, the RNN needs to transmit through many timestamps to learn the semantic relation between these two elements. Besides, because of such a sequential modeling way, each element in a sequence can only learn the semantic relation with its left elements. It means that RNN can only learn limited contextual representation for the sequence. From the perspective of the efficiency, this sequential modeling way makes RNN cannot achieve parallel computing and is impossible to be accelerated by GPUs. Although CNN can achieve parallel computing, it's not suitable to model sequence. The reason is that for each element, CNN only extracts local semantic information for it because of the limited size of convolution can. If we want to learn the contact representation for the sequence, we need to stack INN many times, which makes the model complicated. Therefore, to improve the effectiveness and efficiency of current neural code search methods, we propose a solely attention-based code searching model named SANCS. Our model is mainly composed of two parts, including self-attention networks used to learn the contextual representation for the code snippet and description, and the joint representation network used to learn the internal semantic relation between the code snippet and description. For the self-attention networks, suppose that we get a code vector or a description vector from the word embedding layer. We first transform it to color vector Q, key vector K, and y vector V through three individual linear projections. Then we perform a scaled dot production operation to the color vector and key vector to get a attention weight matrix. Meanwhile, we also apply softmax function to normalize this attention weight matrix. Finally, we get the contact representation for the code snippet or description by performing a dot product operation to the attention weight matrix and the y vectors. By using self-attention network to model sequence, each element in this sequence can pay attention to all the elements in this sentence. So self-attention network needed to consider the distance of the elements and can learn the effective contact representation. Considering that the sequential operation of self-attention network is 1, so like CNN, it can achieve parallel computing and can be accelerated by GPUs. Similar to self-attention network, we can achieve joint representation network by changing the inputs of self-attention network. Specifically, we can use code as color vector and description as key vector and y vector to get the code description attention weight matrix, and use description as color vector and code as key vector and y vector to get the description code attention weight matrix. Through the joint representation network, our model can learn deep-level semantic relation between the code snippet and the description. In this picture, it gives an overview of SANCS. To encode the code snippet, we divided to 3 parts, including method name, API sequence, and code tokens. For each part, we use word embedding layer and self-attention network to learn a contact representation for it respectively. And we concatenate these 3 parts to get the code vector. The same operation are also applied to description to get description vector. Then we get the joint representation for the code snippet and the description by passing them to the joint representation networks. Finally, we train our model by maximizing the quotient similarity between the code snippet and its corresponding description, and minimizing the cosine similarity between the code snippet and its relevant descriptions. We verify our proposed model both in effectiveness and efficiency. We perform all the experiments on the dataset shared by the user of DeepCS. The training dataset contains more than 80 million processed and commented Java methods from GitHub created from August 2008 to July 2016 with at least 1 star. And the testing dataset contains 10,000 Java code query pairs. As for baseline models, we choose DeepCS, a LSTM-based model, and Cocker CNN, a CNN-based model combined with co-attention mechanism. For the effectiveness in this table, we can see that SNCS can outperform DeepCS and Cocker CNN by a variety of 34.8% and 42.2% in terms of recall metric. For NDCG, SNCS outperforms DeepCS and Cocker CNN for 47.1% and 55.6%. As for MRR, SNCS outperforms DeepCS and Cocker CNN 59.9% and 69.7%. It means that SNCS is effective for a code search task. For efficiency in this table, we can see that the training speed of SNCS is 3 times faster than DeepCS, and the search speed of SNCS is 6 times faster than DeepCS. Therefore, SNCS is a more effective and more efficient code search model. This is all I want to introduce. Thank you for your listening.
Thanks for the presenter. Is there any question? Yeah, maybe I have a question. Someone, are you online?
Yeah.
Yeah.
Yeah, I'm online.
As you mentioned in the slide, and you use the water vector to generate the feature vectors of each code, API, token, something like this. And which kind of method you used in water vector? Because there are so many choices.
Do you mean what types of water vector I used?
Yeah.
To be honest, I used the I used the simple water vector layer. Let me think how to say it. I can see by this way. I just use a very simple water embedding layer that provides in the API in PyTorch. I remember this water embedding layer. We can also call it a Glover that proposed by many. To be honest, our key point is the high-level layer, such as self-attention layer. So we just use the simply water embedding layer because it's just can provide a long contextual embedding. Then we aim to do a contextual embedding by our proposed self-attention network and the joint representation learning network.
So were you
Yeah.
finding the word vector during training? Or directly the original one?
Yeah. Just use it. Then, as you know, deep learning just automatically train the parameters.
Okay, thank you. Is there any question
Thank you.
from others? Okay, if there is no further questions, and maybe let's start the second presentation. It's an online presenter. Is Yanjie? Are you online?
Yeah. Hello. I will share my okay. Okay. Good afternoon, and thanks for your participating. Today, I will introduce my work, Icon to Code, recommending code implementations for Android GUI components. First, I will introduce the motivation of this paper. Developing the UI of an app involves two separate activities. The first is design of the GUI, and the second is implementation of the GUI. The latter usually involves the implementation of the GUI interface itself, such as GUI widgets details, layout, constraints, and handling of user interactions, such as what happens when the button is clicked. Take this figure as an example. It is a typical GUI page extracted from an Android app. As highlighted, this GUI page contains various GUI components referred to these icons. Each of these icon GUI components must take user inputs, such as a click or other interaction, and respond accordingly. For example, when users click the profile icon on the top left, a new page will be switched to. Such behavior changes driven by user inputs are usually done by callback methods. Ideally, each icon should be associated with at least one callback method. So our tool is to help developers implement those callback methods associated with these Android GUI icons. The figure presents an overview of our tool. Its three key modules are Database Construction Module, DCM, Similarity Calculation Module, SCM, and API Recommendation Module, ARM. DCM takes APKs as input, and the output is a database mapping icon to API. SCM takes the database and icons as input and output some similar icons. ARM will generate the recommended API candidates. Next, I will introduce each module separately. The first module, DCM, aims to pre-analyze a broad set of Android apps to construct a database, mapping icon to its code implementation. The figure shows the working process of DCM module. The pre-processing step is to extract useful information, such as the icons, to prepare for further analysis. When disassembling Android APKs, we also pass the manifest file to extract the targeted SDK versions. This information will be used when recommending APIs for Android apps under development. That is, the recommended APIs should align with the targeted SDK versions of the target app. And the code analysis step aims to establish a mapping from icon-bound GUI components and their corresponding callback methods that respond to user events. To achieve this, next, I will answer the following two questions. how icons are bound to GUI components on an app UI page, and how can callback methods be associated with GUI components. The first question, we analyze how icons are bound to GUI components on an app UI page. We observe that icons are generally bound through XML attributes in the app's layout configuration files. For example, 1, the source of an image view. And example 2, the background image of a button. Yeah, the listing shows the examples on line 2 and line 8. The table on the right summarizes the list of all the attributes we have considered in this work. And after locating GUI components, the second task is to infer their associated callback methods. Callback methods can be connected with GUI components in 2 different ways. The first is like the bindings between GUI components and the icon files. Callback methods can be specified through XML attributes too. Line 5 of the listing demonstrates such an example. This type of binding can be easily resolved by passing the layout configuration files. And the attribute Android onClick and line 5 specifies the callback method, also named as onClick, that is triggered if the image view is clicked. And the second way, instead of using the XML attribute, developers can leverage code as shown in this listing to achieve the same purpose. In most cases, the callback methods are added following the creation of a GUI component. Find view by ID and line 4. And by connecting those statements, we can eventually make a mapping from icon to their dynamically defined callback methods. And the third step, call graph construction, it is based on the mapping from icons to callback methods. We then harvest the set of APIs accessed by the aforementioned callback methods and consequently build a mapping from icons to their corresponding set of APIs. They are called when the icons receive user inputs, such as being clicked. As shown by our motivating example, it is not straightforward to achieve this. A given callback method may access a set of other methods, and each can invoke a set of APIs. We resort to static code analysis to construct call graphs to ease the extraction of APIs. For each callback method that we consider as an entry point, we construct a call graph for it with nodes and edges. And the last step of DCM module database construction is to build an icon to API database. Okay, now I will introduce the second module, SCM. Given an icon as input, SCM will locate similar icons from the pre-built icon to APIs database. We rely on straightforward approaches to measure the similarity of icons, that is, by image similarity and text similarity. We make use of 3 image similarity calculations algorithms to form a hybrid method. And to ascertain the similarity of 2 text strings, edit distance is a widely used method that computes the minimum number of edit operations required to transform one string into the other. Levitin distance is such a type of commonly used edit distance. We aggregate these 2 similarity calculation algorithms to compute the overall similarity of 2 icons via this formula, where alpha and beta represent the width of same image and same text, respectively. The image similarity is calculated via the icon files themselves, and for the text similarity, we have identified three main sources that provide alternative text to icon-bound GUI component. The three main sources are S1, the icon's reference name, and S2, the ID name of the view, and S3, the alternative text defined via Android content description or Android text XML attributes. And the last module, ARM, will output a list of API candidates. ARM module leverages the traditional collaborative filtering algorithms to recommend API usages. In our tool, an icon plays the role of a user, while each API plays the role of an item. And based on the most similar icons returned by the SCM module, our tool first determines the number of APIs accessed by the associated callback methods of the selected icons, and then models them into an encoding matrix. The probability of recommending a given API to the icon under edit can be calculated. And the output of our tool will be a list of Android APIs that are ranked based on the calculated scores. In addition to the API itself, we also provided the code snips related to the API. Our tool records completed API usage examples into the dataset too. This figure shows a concrete example where the icon under development is used to rewind to the past during data selection in a calendar component. The top left box shows the 20 neighbors based on image similarity returned from the training database, while the top right box shows the 20 neighbors obtained through text similarity. Although not all the neighbor icons are closely similar to the target icon, the top ranked icons such as 1, 2, 3 are very similar to the targeted one, and all of them are also relevant to data manipulation. And about the evaluation part, we give 4 research questions. The first one is how accurate is icon to code in recommending API calling code for GUI components of Android apps under development. And the second is, do the number of the most similar icons and their corresponding code implementations selected for learning impact icon to code's performance? And third one is, to what extent do different ways of text image similarities impact the performance of icon to code? And the last one is, will the performance of icon to code be impacted by the number of APIs accessed by icons selected for training? So the evaluation part, we leverage the commonly used success rate and hit rate metrics to assess the usefulness and effectiveness of our approach. We built a benchmark database with 47,827 icons from approximately 5,000 apps. Based on the default parameters of icon to code, we perform experiments with the standard 10-fold cross-validation procedure. This figure shows our experimental results, including success rate as well as hit rate concerning a different number of recommended APIs where n belongs to the set 1 to 20. when only one API is taken into account, icon to code can already achieve over 50% of the success rate. If we increase the number to 20, the success rate can reach over 90%, showing high performance to be applicable in practice. And then we experiment to answer the question, does the number of similar icons selected for learning impact the performance of icon to code? Our results show that the number of selected icons indeed impact the performance of icon to code when it is small. Well, when the number reaches a certain threshold, the impact tends to be marginal. And the third research question is, to what extent do different ways of text-image similarities impact the performance of icon to code? And the results shows that developers can also resort to alternative text to help find similar event handler callback methods. In the absence of icon images during design, developers could potentially leverage our approach to select suitable icons. Okay, that's all. Thank you.
Thank you for the presentation. Is there any question from the audience? Yeah, maybe I have a question. I'm not the expert related to your work, but I'm wondering, when you design the architecture, you first use the similarity. I mean similarity calculation, and then use the recommendation module. I'm wondering why not directly select the most similar code to relate to the icon. Why you use why instead you use the recommendation training module to choose?
Yeah, the SCM similarity calculation module is just select the most similar icons from all of the icons we collected from the apps, and then the output of the similarity calculation module are the most similar icons, and then these icons they are taken the input of the recommendation module, and then the recommendation module will get some scores for each similar icons and select them. And just leverage the collaborative filtering algorithm to get the most approximate API candidates.
Oh, okay. Thank you for your explanation. And where the choice of alpha and beta differ from different data set?
Yeah. We also did some experiment to change the real value of alpha and beta. Yeah, I think maybe it depends on the quality of different data set, maybe.
Okay, thank you.
Thank you.
Is there any further question?
Hello. Yeah, can I ask a question? So I'm wondering whether the application domains would influence your score. So you collected 5,000 apps. I would like to know which type of apps. I assume if it's text reading, and the interface would be different from games.
Yeah. Actually, I selected the Android apps randomly, but I filtered the apps that didn't contain any icons or less icons. Yeah, I kept the apps contains more than 5 icons in the PNG format. Yeah.
Did you analyze the categories of the apps you collected?
No.
Oh, okay. Yeah. So maybe interesting to have a look.
Yeah.
Thanks.
Thank you.
Yeah, thank you. If there is any further question, maybe we will move to the third paper. The third paper is, is adaptive code completion with meta learning. Yeah, maybe let's start.
Hello everyone, my name is Feng Yu. Today my topic is adaptive code completion with meta-learning. This is my content, and first I will give an introduction. In the field of software engineering, developers have always been concerned about how to improve their development efficiency. Code completion can effectively recommend the next code token, reducing possible spelling errors and effectively completing some repetitive input and improving development efficiency. Early completion methods mainly used manual input heuristic rules combined with static analysis to complete the input code, and almost did not consider the source code's statistical pattern. In view of these problems, Broch proposed the concept of intelligent code completion and mined general code patterns in massive code repositories. Indo first proposed to treat the source code as a special natural language and use the statistical language model in natural language processing to complete the context code. It predicts the token that may appear next by counting the regularity of different tokens appearing in the context. With the construction of large-scale corpus and the development of machine learning, researchers began to use neural network-based natural language models for code completion. These models can learn the code patterns in the massive code data in the open source repositories and make more effective use of code semantic and structural information. However, the characteristics of these natural language corpora are not always related to source code. Therefore, the existing code models based on natural language models have some unsolvable problems, like unknown local tokens and unknown local code patterns. For unknown local tokens, like developers create new names for variables, classes, and methods. And for unknown local code patterns, like different developers have different coding styles, experience levels, thus their code patterns will be different. There have been some studies to improve these problems, but they all have defects. First, the most effective research to complete unknown local tokens at present mainly use subword segmentation method and n-gram-based caching mechanism. However, it ignores the syntactic and semantic structure of source code. Second, to solve unknown local code pattern adaptation, code use dynamic setup. Briefly, they split the test project into multiple partitions. And for each test sample, they retrieve the model on the rest files of the same partition. However, this method does not guarantee the prior knowledge being kept after local retraining and may underperform in restricted situations that require a small number of samples for rapid adaptation. Next, I will introduce the methodology of our work. This is a framework. Firstly, construct the code representation graph and the identifier cache through the static analysis and byte-pair encoding of the code. The code representation graph is input into the graph neural network to obtain the list of candidate code tokens based on the open vocabulary. Then the identifier cache is filtered through the attention mechanism to obtain the list of candidate results in the cache. Finally, weighted parameter is used to combine the two candidate result lists to get the final completion result. The above basic model is called code GAC. The following part is procedure of adaptive code completion with meta learning. Sample the local support set and train code GAC with meta learning strategies. So the model can adapt to the local contextual settings in a few short samples. Let's talk about the byte-pair code. This figure shows an example of how Java source code can be segmented into subword units using BPE method. Note that we used a special symbol to mark the end of token so that we can convert from a series of subword units back to a series of tokens. The subword units are adaptively selected according to the frequency of occurrence. The effect of this is a more common mark like public figure. In this figure is assigned the complete subword unit, while a less common mark like initial cap is divided into more common smaller unit. After token level encoding, we need to encode as much related context information as possible. After this method is divided into two steps. The first step is to build the program graph, and the second step is to run the graph neural network in an obtained graph to give a vectorized representation of the context. To build a program graph, we first represent a program source code as a graph and use different edge types to model the syntactic and the semantic relationships between different tokens. Then we add additional edges to connect the different uses of the grammatical tags of variables. Then we introduce the adaptation with meta learning. Here is a pseudocode for our adaptation phase. We use meta learning strategy to train the model. First, we need the base model denoted as theta. M is the iteration times, K is the number of samples, and N is the inner loop updates. For iteration equals 1 to M, sample a target project, set the theta 0 to theta, sample target token T and the corresponding context data. sample support set consists of k support samples in the touch project. For I equal 1 to n, calculate LSI using S and equation 6. Equation 6 is the support loss at step I. Then update theta I with LSI. When the in loop is done, compute the total loss and update the initial theta of original model with loss on the validation set. Then how to get the best top results around? We use a simple single layer GRU as our code. Encoded context vector is input into GRU. GRU can calculate probability for any support unit sequence and then gradually generates a complete token by an algorithm similar to beam search. We also implement a local identifier cache based on attention mechanism. Attentional cache. First, calculate the attention weight of the cache unit. Then use attention weight to calculate the probability distribution of local identifier in the cache in the current context. Next is experiments and results. We first evaluate code GAC of general code completion task and see how to improve local token completion without adaptation. Code GAC has made 2 different improvements to the existing code model. One is combination of BPE and graph-based context encoding. The other one is attentional cache. It can be seen from the table that our method has better performance than other models, among them BPE and sequence-to-sequence uses exactly the same decoder as our method. Is a single layer GRU with the same model size and hyperparameters. Graph-to-sequence also uses a GRU decoder, but it is a token-based vocabulary that has not been processed by BPE and output one complete token at one time. In addition, we compare the attentional cache in code GAC with n-gram cache and the nested cache. It can be seen from the table that after adding cache, the accuracy of the model has been improved to varying degrees. Among them, the improvement of n-gram based cache is the smallest, and the improvement of attentional cache is more obvious than that of nested cache. This table shows our experimental results of model adaptive effect. It can be seen from the table that our meta-learning method has a significant improvement in cross-entropy and MRR performance. In addition, methods involving dynamic adaptation are better than non-adaptive baseline methods to varying degrees, which highlights the importance of dynamic adaptation. And here is the conclusion. Our work proposes a dynamic adaptive code model, meta code GAC, based on meta-learning, and experiments show that code GAC outperform our current state-of-the-art baseline. And second, meta code GAC outperform other adaptive and non-adaptive methods. It can effectively improve local dynamic adaptation performance, and different inner update times and sample numbers have different impact on the performance of the dynamic adaptation.
Okay, thanks for the presenter, Li Yufang. And Li, are you online? Hello, Li. Oh, maybe if there is any question, maybe let's contact the author offline. Then let's start the last paper. It's what makes open source software projects impactful, a data-driven approach. Let's start.
Hello, everyone. I'm Ono here to present our work, What Makes Open Source Software Projects Impactful, a Data-Driven Approach. This work is a collaboration between Tianjin University, East China Normal University, and Singapore Management University. I'm the presenter shortly from Tianjin University. Let's first talk about the background of this work. With the wide adoption and acceptance of open source version control and hosting systems, more and more companies, including Google, Microsoft, Apple, and Facebook, are putting their projects on such platforms, among which the most famous is GitHub. This figure on the left is adopted from GitHub official website, showing year-over-year change in rate of open source project creation, 7 days rolling average. So as we can see, the COVID-19 lockdown gave a rise in the number of GitHub projects created. More and more open source repositories have been created over time. Here is another statistics also adopted from the GitHub official website. It shows the distribution of open source contributors by geographic location over time. As we can observe from the graph, that currently North America occupies the contributors of GitHub projects, and the trend tends to spread all over the world. And in around another 10 years, that is 2030, there will be more contributors all over the world. The influence of open source projects is gradually expanding in the geographic dimension, and it has been reported that most successful open source software projects rely more on distributed testers and debuggers than actual developers. It is thus very important for open source projects to be impactful, by which we mean to attract attentions from the open source development community, so as to gain support on development, testing, as well as maintenance from the community. So, how to make your GitHub project impactful? There has been research on how to make the GitHub projects popular. Most existing work conduct their study on a small data set about popularity, success, and quality of GitHub projects. But there has never been a work which focuses on the aspect of being impactful. This motivates us to study the relationship between GitHub projects and its impactfulness, with the purpose of providing suggestions on GitHub developers to make their projects impactful across the community. So, driven by this motivation, we conduct an in-depth study on this. Our method can be divided into 3 steps. The first step is to define impact of our projects. Later, I will describe in detail. Here, we try to define the impact quantitatively instead of given subjective definitions. And after getting the quantitative definition of impact, we collect a large number of GitHub projects. In particular, we collected more than 146,000 GitHub projects which were created during 2008 and 2018. And we tried to analyze the factors that affect the project impact with data analysis techniques. That's the third step. So let's first look at the steps one by one. How to define impact of a project. Impact of project tend to be subjective. Different person has different perspective about this concept. The impact here in our work, we use it to represent the attractiveness or the ability of the project to attract attentions from the open source community. So instead of taking a subjective definition as has been done by existing related work, we want to be able to quantitatively define the concept of impact. In order to do this, we conduct a user survey with IT developers and researchers from the computer science software engineering community. An intuitive observation of a GitHub project is like this. Here is a screenshot of a GitHub project. And as we can see on the right top of the page, there are 3 tabs showing the number of watch, number of stars, and number of fork. And our intuition is these numbers kind of indicate the impactfulness of a project, because all the stars, the number of stars, number of watches are given by contributors or developers from the community who has by some means know the project or has worked in the project. Based on this observation, of course, this is not only factor that may affect impact, but this is our main observation. And based on this observation, we designed a questionnaire which contains 5 questions, trying to understand what in the participant's perspective affects or is indicators of project impact. So the first 3 questions are trying to help us understand the user profile of the participant, including their occupation, whether they are a student in college, a researcher in college or research institute, or even some companies, IT developers or IT project managers. And the following 2 questions help us understand their experience with open source community like GitHub. In particular, we asked how many GitHub projects they have been involved in the past 2 years, and how frequent do they use GitHub. By those 3 questions, we'd like to observe or understand the profiles of the participants and help us decide whether the person is qualified to answer the question. And the fourth question is to understand the participants' perspective about the 3 factors, that is fork, star, and watch. How do they indicate project impact? And we asked them to rate from 1 to 5, where 1 means little or no indication, and 5 means strong indication. And the last question is kind of open question, where we would like to know what other factors that affect project impact. We give some predefined answers like organization, documentation, connect frequency, release frequency, development framework, or packages used. And we also allow them to specify their particular specific answers. And this is a multi-choice answer, so participants can choose more than 1 answer they want. After the designing the survey questions, we released the survey questions to a lot of our industry collaborators and academic collaborators, and they circulate around their personal platforms. As a result, we were able to collect survey results around 260, among which 253 are valid survey results. And these survey results were collected during a period of around 2 weeks. Here is the statistics of the survey results. As we can see from the table where Q2, 3, 4, 5 represented the particular answer for the 4 questions, and the row here, SRDM, indicates the occupation of the participant, but that is whether she or he is a student, a researcher, a developer, or a manager. So TT here represents the total number of each category. So as we can see that we received 253 valid surveys. We manually filter out those surveys that didn't answer the required field. And as we can observe that more than half of the participants are from industry and they are software developers. As for the second question, that is how many GitHub projects have they contributed in the past 2 years? Most of the participants who are involved contributes to more than 4 projects in the past 2 years, which means they are quite active in the community. The third question is about how frequent the participants visit GitHub. We can observe that like more than 199 of the participants at least visit GitHub every other day. So, which again means they are quite active in the community. The fourth question is about the rating on Fork, Start, and Watch. And here we have a pie chart which more clearly shows the results. So the first pie chart is about Fork, second is about Start, and third is about Watch. So as we can observe, there are more than 60% of participants rating Fork as highly indicative of factor, that is for rating 4 or 5. And this number is about 50 for Start, and is about 41 for a Watch. And around 23 to 27% of persons give moderate ratings, which means moderately indicating the impact. And only 15% of the participants believe Fork is less indicative of impact. This number is around 25 for Start and 31 for Watch. So given this statistical results, we based on the survey result further give a quantitative calculation of impact. So particularly, we use this formula 1 to calculate the factor of each of the previous surveyed, the previous surveyed factors, Fork, Start, and Watch. So here, the small f represents it is either a Fork, Start, or Watch, and the Li represents the frequency. Li represents the as participants, the rating for the factor f. So with this Fi, they represent the normalized importance of each factor f, small f, indicating project impact in each response I. So after this calculating we further calculate VF, where it represents the calculated weightage for the factor F, where small f also belongs to star or watch. So this is the weightage that we're gonna to use in our final calculation of the impact. So here I indicates the impact of a given project, and here FSW represents the number of walks, number of stars, and number of watches for this project. And here the 0.364, 0.306, and 0.3 are the weightage for each of the factors that are calculated based on the formula 2. So this formula 3 gives us a formal way, a quantitative way to calculate the impact of projects, where the weights here were calculated based on the survey results that we have collected. So after formally define what is a project impact, the second step is to collect enough GitHub projects to do the data analysis. Well, we follow standard to collect GitHub projects with the GitHub API, and we collect in total 148,000 projects. And our collection, since there are, I think, more than 148 million projects in GitHub during the time we were collecting data. We were unable to collect all of them. So in order for our collected projects to be representative, we actually random sample one project ID from per 1,000 projects, and in this way we are trying to mimic the project distribution in GitHub projects. So here is the statistics of the collected projects, the features of the collected projects. So as we can see, we have collected features like related to the project contributors, the number of contributors, and the average followers means the number of followers of each contributor of the project, average follower of contributors of the project, and average following is the average number of the other contributors that the contributors of this project following. Excuse me. And we also collect information related to documentation of the projects, like whether this project has a README profile, the size of the README, the URL numbers, number of URLs in the README file, and whether the project has a wiki page. Except for that information, we also collect basic information about the project, like the number of branches, number of commits, the number of issues, releases, the size of the project, etc. And in particular, we calculate the creation year of the project, as well as the active duration of the project. That is, how many years has the project been active since it is created. So these are all the features that we collected, and we use these features for the later analysis. So as a last step, we conduct analysis on the collected project features. So the question we want to answer is, what are the GitHub project features which separate impactful projects from those not impactful projects? So our the first method that we used for the analysis is a correlation coefficient analysis, where -1 represent negatively correlated, 1 represent positively correlated, and 0 means no correlation. So in particular, we adopt 3 most popular correlation coefficient analysis methods that are the Spearman, Pearson, as well as Kendall's talk correlation coefficient analysis. So the correlation analysis gives us a direct result about how 2 factors are correlated. And we also conduct classification analysis with, in particular, we adopt the random forest and sequence models to build the decision tree, based on which we can observe what factors combine together that affects the project impact. So let's talk about our analysis results. First, about the correlation analysis results. So as the 3 correlation analysis show consistent results. So we just use the Spearman correlation to show the results. So as we can observe from this figure here, so here we have 17 features, and the last row NP represent the impact. So as we are interested in seeing what factors affect project, what factors are correlated with project impacts, so we can only pay attention to the last row or the last column as they are symmetric. So as we can observe from the figure that here the issues, number of issues the projects have has the strongest correlation with project impacts. And other than that, number of commits, number of contributors, whether it has a copyright information, here the URL number, as well as the number of years that the project active, also has strong correlation with positive correlation with project impact. Interestingly, here the orange color here, it represents a negative impact. Okay, so as we can observe that its fork, this factor is negatively correlated with project impact. So its fork here means whether the project is forked from another project. So it seems that the forked projects are less impactful. Here is the decision tree plot based on the C.5.0 classifier. So there are 2 kinds of nodes. The ellipse are the intermediate nodes, and the buckets here represent the leaf nodes. And in buckets, we actually divide our projects into 2 categories. One is impactful projects, and the other is not impactful projects. So here the non-event represent the non-impactful projects. So here in the buckets, the light color represents in the portion of impactful projects, and the dark color represents the portion of non-impactful projects. So from the result, we can observe that the number of contributors actually has shown strong positive effect on project impact. So we can observe from the bucket 29 here. The decision conditions are labeled on each branch here. So when contributors are greater than 14, we can see there are a large portion of projects which are impactful. So we can also see from bucket 3 and 5, the combination of issue and contributors may also have a negative effect on project impacts, because when you have small number of issues and small number of contributors, the project can tend to be less impactful. Another observation is that The README file with detailed contents show positive effect on project impact. So here we are using the R size URL number to represent actually whether the detailedness of a documentation. So as we can see, if you have small URL numbers right here, the project tends to be less impactful. And if the document size is large, you have large URL numbers, it tends to be an impactful project. So these are the main results that we observed from the decision trees. And based on the empirical results, actually there are some more details about the analysis results, such as the feature importance ranking based on the random forest model, as well as the C.5.0 model. For interested readers, please refer the details in our paper. So to conclude, based on our analysis results, we can provide the following actionable suggestions of making your GitHub project impactful. First, more contributors. It seems quite intuitive. Here means more active contributors that are the second factor is the contributors better be with more followers, which is also cannot be intuitive because if a contributor has more followers, that means he himself or herself is actually an impactful person. And the third is maintain detailed documentation, which is quite obvious from our analysis results. If you have better documented, you have a long documentation with more URLs connecting to the other outside links, web pages, and especially if you have wiki pages, the project tend to be impactful. The third suggestion is being active. So better frequently or actively maintain your GitHub project in order for it to be impacted. And the next point is differentiation of projects. So this is from our result that forked projects tend to be less impactful, or it has a negative correlation with the impact of projects. So maybe originating your own project is another way to make your project impactful. But all the factors here, they may be combined together to make your project impactful. Like none of them can individually decide or the impactfulness of your projects. So this is the main results of our work and my presentation.
Okay, thank you for the presenter. Is there any question from the audience? And I have a quick. Sean, are you online? Is there any author of this paper online? Oh, okay. Maybe if there is any further question for this paper, feel free to contact the author. So I think it's the end of this session. Thank you for attending the software mining session. Let's have a 10 minutes break and go on next session. Thank you again.
Hello, Bowen, are you here?
Hello.
Okay. Bye.
Yeah, I'm here.
Okay, good afternoon, everyone. It's time to the next session. And the topic of the next session is about the system. And I'm the chair of this session. My name is Sen Chen. Currently, I'm an associate professor of Tianjin University, China. And today I will chair this session. And our session also includes 4 papers. And for the first paper, the speaker will talk their presentation online, and for the 3 other papers, I will play the prepared videos for them. And after each presentation, we have 2 or 3 minutes to ask the question for the speaker. Okay, let's start. The first speaker is Bo Wenyan from University of Chinese Academy of Sciences, China. And the paper title is Hammer's Efficient Cache Management for Container-Based Serverless Computing. And Bowen, if you are here, you can start now.
Okay. Can you all guys hear me clearly?
Yes.
Okay, let's begin. Hello, everyone. I'm Yan from University of Chinese Academy of Sciences. I'm gonna introduce the work Hermes, the efficient cache management for container-based serverless computing. Serverless computing is another popular trend in
Hello, Bowen. Bowen, are you here? Kanjie, can you hear me? Okay, I think Bowen is offline. Let's move to the next talk first.
Hello.
Okay, Bowen.
Okay, I have just sorry about that. I have just lost the connection.
Okay, you can connect again.
Okay, I began for where we're starting. Sorry about that.
It's okay.
Okay, serverless computing is another popular trend in the current cloud computing field, which frees users from the trouble of managing servers. At the same time, serverless computing provides users with a more fine-grained building model. In the function as the service incarnation of the service model, the smallest unit of calculation used is a service function written by the user. When the serverless computing platform receives a service request or a predefined event is triggered, the serverless computing platform will deploy and initialize a temporary execution sandbox and run the function uploaded in the sandbox to process the request. After the execution, the sandbox will be destroyed and the occupied resources will be recycled for the next request. Serverless computing is wonderful, but there are also opening challenges in this field. Long deployment latency is one of them, before the platform executes the container-based function, they have to pull container images to local disk from a remote registry, which usually takes more than 1 second for a heavy function. And those deployment processes take more than 90% of all time in our evaluated cases. And service workloads have frequent updates. Developers may update the function many times based on their need. Platforms have to pull updated images every time, causing an unacceptable time consuming before the execution of functions. And this figure shows the default disk-based, fully local caching mechanism by Docker. The remote registry is a remote server storing images of serverless functions. While receiving a function request, the container engine on a selected worker node pulls the image from remote registry or loads the image from local disk. The necessary data for starting the container is loaded into memory and may be evicted by the system. Pulling the full image has a serious impact on the deployment efficiency of the serverless functions. And this figure illustrates an improved memory-only image loading mechanism, which are based on the on-demand pooling technique. While receiving a function request, the container engine loads the necessary data in the image on demand and directly from remote registry, which eliminates the pooling process. The remotely fetched container data is cached in memory for all the containers on a machine. The local disk is left unused, and the evicted data is abandoned and reloaded remotely. While this mechanism is realizing a satisfying performance for simple workloads, in a machine where massive function requests arriving simultaneously, the image data may be repeatedly reloaded from remote registry, since data page caches in memory may be frequently evicted, which seriously impacts the deployment and runtime performance. The design of Hermes is based on two observations. Firstly, there is only a small fraction of image data is needed during the execution of containers. Therefore, we use the on-demand technique to speed up the pooling process. Secondly, the overall performance can benefit from the local cache of image data. So a fine-grained image data management mechanism is proposed to eliminate the problem of data reloading and also to improve the runtime performance of functions. The basic idea of Hermes is what we called a partial local caching image loading mechanism. The image data is loaded to the memory on demand and is swapped to the local disk after being evicted. This figure shows the overall architecture of Hermes system. Hermes leverages a shared storage to store the layers of images. Rather than pulling full image data from remote, the images is located on the remote storage and can be loaded by the containers directly. A mapping structure will be constructed and stored on local disk, which helps serverless functions load the data on demand from the remote storage directly to the memory. To further improve the performance of serverless functions and to eliminate the reloading problem, Hermes employs a two-level caching strategy to manage the memory effectively during the execution of service functions. The first level of caching strategy optimizes the memory cache through a weight-based ARU algorithm, which uses the parameters generated in offline profiling and online controlling stages to prolong the period that data stay in memory. The second level of caching strategy eliminates data reloading of service functions by writing evicted page caches to the local disk. When the evicted data is requested again by a container, it can be reloaded directly. When Hermes receives a function request, it initially fetches the manifest of the image from repository and retrieves the layer information from the manifest. Once having the layers located on the remote storage, Hermes makes references of the layers on local disk, recording specific locations of different layers in the remote storage, which can help service workloads or functions quickly find the required data. This mapping information is pinned to the memory to accelerate the processing of I/O requests to the layers. Cache Manager adopts a weight-based ARU algorithm to managing the page cache. While the metadata of images is pinned to the memory, Cache Manager establishes the weight of the cached files combined with static and dynamic weight generated from offline profiling and online controlling, and adjusts the expiration timeout of data staying in memory, which enables container data to be kept in memory much longer than temporary data, realizing a better cache efficiency and benefits to the overall performance of the entire system. In the stage of offline profiling, Cache Manager periodically scans all the images, retrieves layers information, and constructs the dependency graph G. Each node in the dependency graph represents a layer, and each directed edge represents a dependency from layer A to layer B. Cache Manager calculates the static weight for all the layers based on the depth of the layer and saves the result into files on local disk. After a file is loaded into the memory, it inherits the static weight from the layers it belongs to. After the offline profiling procedure, every layer is assigned a weight value, and the values grow larger for lower layers, which may be accessed more frequently during the execution and therefore should be kept in memory longer than other data. In the stage of online controlling, Cache Manager calculates the dynamic weight for cached pages it monitors. It monitors the file access requests of running containers in real time and calculates the dynamic weight of the page being accessed based on the access frequency. After calculating the dynamic weight of the page, Cache Manager calculates the final weight of the page using the static and the dynamic weight, and the page will be linked to the corresponding page list according to its final weight. Cache Manager periodically scans all pages in the page list, invoke mark page accessed system call on each page. The main purpose of this function is to mark the page as recently visited, making this page less possible to be evicted by kernel, therefore improving the cache efficiency of service functions. The weight of a page indicates the number of times that this page needed to be set by the function. Each page will have its weight after a scan period, and finally leave the page list in order to avoid occupying memory space permanently. The cache manager monitors the eviction of cached pages in kernel and asynchronously writes the page about to be evicted to the local disk and make a reference to record the relationship. The references are persistently cached in memory to accelerate the reloading from local disk. When the serverless functions access the corresponding data again, the cached data in the local disk will be loaded into the memory directly, avoids the reloading of data. In the evaluation part, we use 5 identical physical machines to test our system. We also test the default approach, the Dragonfly, and the Slacker as the baseline systems. And as for benchmarks, we select 4 serverless workloads from the open source project Function Bench. We have had several evaluations in our paper, and I will focus on the first 3 topics in this talk. We deployed containers of different workloads concurrently on the test platform with equal shares. The number of containers deployed ranges from 10 to 300, and containers in a specific round are deployed concurrently. The test result shows the average time for all the containers to launch under different concurrency conditions. Hermes significantly outperforms the default approach and the Dragonfly in all cases, and has a better performance against Slacker in high concurrency scenarios. Hermes minimizes the overall deployment latency from 15% to 60% on average when deploying 300 containers. We deploy and started different service workloads on one node. We recorded the total amount of data transferred through network during deployment and execution. The number of containers of different workloads is 1,500. Compared with other approaches, Hermes can reduce data transmission by more than 90%, and the problem of data reloading is completely eliminated due to the optimized cache management strategy. We tested the execution latency of different workloads. The latency is defined as the time interval from the start of all containers of workloads to the end of execution. The number of containers deployed ranges from 100 to 300. Images are downloaded to local disk in advance for default approach and Dragonfly, while Slacker and Hermes still yield the on-demand data loading mechanism. The result shows that Hermes has obvious better performance in all test cases. In the test cases of float operation and impact, Hermes is 2 times faster than default approach and Slacker, and Hermes is 5 times faster than the default approach and Slacker when running the MapReduce and the image processing workloads. In conclusion, we propose Hermes to fully implement 2-level caching strategies by persisting metadata cache and prolonging the lifetime of file cache along with swapping evicted file cache with local disk. It can minimize the network traffic during the execution of serverless workloads efficiently and decreases the execution latency. That's all the content of my talk. Thanks for your attention.
Okay, thanks for your nice talk. Any questions for the speaker? I think you can answer, ask the questions directly. Okay, I have a question for you. In terms of the efficiency, I think your approach achieves a great performance compared with other approaches. But what are the limitations for your approaches from other aspects?
So what other aspects? I don't fully understand this.
I want to know some limitations about your approaches, because I think you achieve a great performance compared with other approaches in terms of their efficiency. But any limitations about your approaches, you think?
Oh, well, limitations. So we just, you know, in the starting of serverless functions, there are two main parts. The first one is the deployment latency, and the second one is the startup latency of the serverless functions. Those two parts together combine together to well, so they are also important, the most important parts. So we Hermes, so our system just eliminates or just minimize the first part, of the latency, and we just don't minimize the startup latency of the service functions.
Okay. Okay, thanks. Thanks again for your talk. Due to the network traffic, I think we can talk about offline. Thanks again.
Okay.
Okay, let's move to the next talk. The next paper is simulated or physical, an empirical study on input validation for context-aware systems in different environments. And the speaker is Jinchi Chen from Nanjing University. And I think I can first play the prepared video for this presentation. Can you see my screen?
Hello, welcome for joining this presentation on our paper titled Simulate or Physical, an empirical study on input validation for context-aware systems in different environments. I will introduce the background of the question, including context-aware systems and input validation for it. Our approaches include a testing platform for CAS called RM testing and the evaluation based on it. The developing of context-aware systems echo the vision of Internetware by integrating cyber and physical space. These systems continually sense environmental changes, make decisions based on the pre-programmed logic, and then take physical actions to adapt to the changes. Typical CAS include unmanned aerial vehicles, self-driving cars, robots, and autopilot. However, empirical evidence shows that building CAS is challenging and easily error-prone, such as the crashing of Tesla's self-driving car and falling of the autopilot program of Boeing airplanes. One of the reasons is that these programs have to adjust the complexities during their interaction with the physical environment. For example, uncertain inputs from the physical environment are unpredictable while developing a CAS, and they could lead the system to failure. Therefore, There is a strong need for validating the input of CAS to prevent them from entering fatal errors. Many works have been devoted to make CAS more reliable. For verifying CAS, some model-based approaches were proposed to find counterexamples that violate certain properties. For testing CAS, some code-based approaches were proposed to explore a CAS various behavior. And for input validation, there are some database approaches to determine whether an input could lead to abnormality. However, one of the main difficulties towards reliable CAS is that it requires the engineering efforts to implement and evaluate approaches in the real physical environment. According to our literature review, only 17% of published work use physical environments, which exactly align with a recent survey. The survey attributes this phenomenon to the cause of real-world experiments. So there will be a natural question. Is the simulate-based evaluations sufficiently demonstrate the approach's effectiveness? The major challenge to answer this question is to build a testing infrastructure in physical world for testing CAS. Building such a testing platform also requires efforts on implementing the software modules that support testing and validation approaches. To answer this question, we select self-driving program as the target subject. Self-driving program is one of the killer applications of CAS. The main reason for this selection is the giant gap between simulate-based academic research and real-world-based industry practice of self-driving program. For example, about 80% was in autonomous driving system check of EC20 are simulate-based, while autonomous vehicle testing by California DMV is real-world based. We also evaluate 3 input validation approaches, including inconsistent context checking, uncertain environment checking, and deep learning model input pruning. These approaches validate the environmental information pushed to the subject program and filter uncertainty's impact on a program's input. They are likely to be affected by different environments. For example, the predefined input may be different from the real-world input, and the randomly generated uncertainty may also be different from the real-world uncertainty. Among these approaches, inconsistent context checking validates the restrictions on the relationship between multiple pieces of context. Uncertain environment checking checks whether the system surrounding environments will enter abnormal state soon. And deep learning input pruning distinguishes and prunes the inputs that exceed the model's handling capability. In conclusion, we address these challenges by building a testing platform called RM testing and implementing 3 input validation approaches in both the simulate and physical environments. RM testing was developed based on a refitted DJI RoboMaster RoboCar. To better answer the research question, we also conducted experiments to evaluate the difference between the approach's effectiveness in the 2 environments. Here is the architecture of the platform. Basically, the platform connects a DJI RoboMaster S1 RoboCar and a subject program under test. The platform mainly consists of 4 parts, namely sense, control, input validation, and info. Among them, The sense part enables the subject program to sense the robot car's surrounding environment. The control part controls the robot car to move and rotate. The input validation part implements the aforementioned approaches, and the info part records the running logs of the system. Since RoboMaster S1 is only equipped with 4 context sensors, we also install range sensors in the forward, back, left, and right of the robot car to enrich its sensibility. The range sensors obtain the horizontal distance between the robot car and the other objects. All sensor reading data are sent to a computer for further processing. Besides the sensor data, we also modify the robot car's FPV controller to enable the self-driving program acquire the FPV camera's images. The self-driving program can use encapsulated methods to control the camera to better monitor its surrounding environment. For the constraint checking module, we implemented and modified the ECC approach for constraint checking. We designed specific constraints that are effective for the robot car scenery based on previous work. An effective constraint needs to deal with errors that occur frequently in the scenery, so that they can efficiently improve the quality of validated context. In addition, the constraints should avoid missing detection and false alarms. Thus, in order to design effective constraints, we first check the execution trace of the robot car and analyze main reasons for its failure. Here are the constraints we use in the system. These constraints are mainly used to alleviate problems like random errors and sudden changes due to changing sensor failure. Where a constraint is found to be violated, we repair the consistent error with job lattice strategy. For the invariant checking module, we implemented and modified the call-me approach for invariant checking. The main challenge to applying call-me approach is to design effective invariant template. Similar to the designing of constraint template in constraint checking module, we observed execution traces of the robot car to determine the template of the environmental invariance. We also optimized the settings of the invariance parameters to make the generate invariance neither too general nor too specific. Here are the templates we used. These invariants mainly focus on preventing the car from crashing into any obstacle. For deep learning model input pruning module, we implemented and modified the dissector approach. With the original approach, there is a fixed threshold to determine whether the input image is valid and drops the invalid ones. In some situations, such a fixed threshold could lead the self-driving program to drop all received images during a period of time. So we perform the approach on 5 images at one time and choose the one with the highest score. This is the overview of our empirical study settings. The subject is a self-driving program. The scenario is an urban road network. We ran the subject program with different configurations, which enable or disable each input validation approach, and finally calculated the success rate of the robot car reaching specific places. The scenario we designed is a static urban road network, which consists of straight roads and intersections, simulating the real world. Here is the design of the map. To simplify the scenario, we designed the map according to 3 principles. All roads have the same width, all roads are on the same plane, and all intersections are one of 3 predefined types. So any 2 roads are vertical or parallel. We constructed the scenario based on the map in the physical and the simulate environments, respectively. The simulate one was constructed with the Unity engine. Here are the configurations of the experiments. They are divided into 8 groups, including one group that disable all 3 approaches, one group that enable all of them, and 6 groups that only enable part of them. To better answer the research question, we conducted 2 experiments. In the first one, the robot car was initiated with a perfect start state and tried to reach and pass a specific intersection. In the simulated environment, the ending point is the 15th intersection. In the physical environment, the ending point is the 7th intersection. In the second experiment, the robot car was initiated with a deviated start state and tried to pass the first intersection. Here, deviate refers to both random displacement, deviation, and angle deviation. The second experiment helped us better study the effectiveness of constraint checking and invariant checking from a more fine-grained perspective. Our empirical study shows that the input validation approaches are effective in both the simulate and the physical environments. More specifically, with the help of these approaches, the proportion of the robot car passing the 15th intersection in the simulate environment increased by 82%, and that of passing the 5th intersection in the physical environment increased by 50%. We also find that these approaches are more effective in the simulate environment. With the help of them, only 24% can reach the 6th intersection in the physical environment, while 82% can reach the 15th intersection in the simulate environment. These input validation approaches are effective from the perspective of each approach. The success rate of experiment 2 increased by 9% with constraint checking enabled, increased by 26% with invariant checking enabled, and the accuracy of image classification increased by 1.6% with deep learning model input pruning enabled. So the answer to the research question is that the approach's effectiveness in the physical environment is not as significant as that in the simulate environment. Context-aware system-based works should be evaluated in the physical environment in order to demonstrate their effectiveness and usefulness. Thank you for your listening.
Okay. Jinqi, are you online?
Yes.
Okay. Any questions for Jinqi? Okay, actually, I have a question for you. According to your presentation, I know that there are some gaps between the simulated and physical environments when conducting experiments. So, do you have any suggestions to mitigate such gap between simulated and physical environment when we conducting the corresponding experiments? Jinqi, can you hear me?
Sorry, I didn't get it. Can you repeat it?
My question is that do you have any suggestion to mitigate the gaps between physical and simulated environments when we conducting the experiments? Oh,
我需要做过的。
okay, I think we can talk about more detail.
Yeah, I'm here. The major gap between the physical and the simulated environment is that we first, you know that when testing something, testing a program in the simulated environment, we actually get the full controllability and observation of the program states. For example, we can get every variable's value at any moment if we fetch the variables from the memory. But however, in the real world or in the physical environment, that observation of the program's execution state is not always available. For example, considering our robot car example, in the simulated environment, we can always assume that the car's direction, speed, and location is available. However, in the real world, we cannot make such assumptions because get the car's speed, for example, requires additional testing infrastructures, such as something like the speed ratio or something like the camera that catch the car's movement. So the first thing is that we have to enable the testing infrastructure's observation on the program state. And another thing is that we have to make the program controllable. In the simulated environment, a program state, we can directly set the program state to a desired variable. For example, if we want the program get a test input of 1, we can directly set the corresponding variable to 1. However, in the real world, you cannot just have a 1 into the car to make it sense distance towards the forward obstacle to 1. So we have to make the program's sensing towards its surrounding environment control. So this is the major gap between testing a program in a simulated environment or a physical environment, the controllability and the observability.
Oh, I see. Thanks for the detailed answers. Thanks again.
Okay.
Okay, let's move to the next talk. And the next talk is from Yuexin Huang from Beijing Advanced Innovation Center for Big Data and Brain Computing, China. And the paper title is Best Answers Prediction with Topic-Based GAT in Q&A Sites. And I also play their prepared video first.
Yuexin Huang from Beihang University. I will introduce our work, Best Answers Prediction with Topic-Based GAT in Q&A Sites. First of all, let me introduce a problem we dedicate to solving. Users of large question and answer communities, such as Stack Overflow, are facing a data overload issue. As we can see from the left side picture, the number of daily questions has soared to about 6,000, as these questions are displayed in a question list. And we can see from the right side picture, this is how the question list look like. And for community users, it takes time to find a proper question to answer. At the same time, there are more and more unanswered questions, and we counted the average number of views for unanswered questions. The result is 237, which is unusually low for a community with about 10 million users. So it's necessary to route the right question to the right user. The object of this work is to design an approach to find the best answers for the question. There are many related researches dedicated to solving this problem, and they can be roughly divided to 3 categories. First one is the similar question matching-based approaches. They find the existing questions in the community which is similar as a new one, and they recommend the answer of the existing question to the new question. The second one is a user profiling-based approaches. They abstract user feature from the history documents of users and use it to match with a new question feature. And many other works find that collaboration information of community users is helpful for best answers recommendation. And now let's talk about our approach. This is the framework of our approach. As we can see, there are 3 steps. Step 1, user profiling and vectorizing based on the community data. Step 2, we need to pre-process the new question and vectorize it. Step 3, we calculate matching score between the new question and the users, and based on the result, we do the recommendation. Firstly, let's take a look at the user profiling steps. As we can see from the picture, there are 3 steps to create user profile. Step 1, we establish a model based on users' historical document, and the result can be used as user primary works vectors. Step 2, collect historical question and answer records and construct a user collaboration matrix. Step 3, based on the graph attention network model, we use user collaboration matrix to optimize users' primary vector. I will introduce all the steps one by one. But before that, let's take a look at the format of Stack Overflow data. A question text consists of 3 parts: title, body, and text. Title is a general description of the question, which is more concise. Body is a specific description of the problem with a lot of natural language. It also contains some code information. To pre-process it, we remove the code and the stop words in it. As for text, we just need to stem in. After the pre-processing, we merge the 3 parts of the question together as one document. Then we use all the documents in the community to train the LDM model. After that, the user-related documents are collected as user history document. The trained LDM model will vectorize the user history document and produce the user primary vector. However, part of users don't have enough history documents, so the model result may not be accurate. We consider using the information of collaboration to optimize our user primary vector. In order to build a collaboration network between users, firstly, we use communities' question and answer records to build a user question interactive network, just like this. And then we establish a user collaboration network based on 2 relationships. One is the ask-answer and another is a call-answer. Based on the 2 relationships, we construct our user collaboration network and then represent it by the adjacent matrix. According to our observation, the original user collaboration network is relatively sparse. According to the related researches, we built a two-order collaboration network to alleviate the impact of sparsity. The construction process is shown in the picture. On the basis of the original one-order collaboration network, if two nodes are connected to the same node, such as the user A and the user C connected to the user B, and we add an edge between these two nodes, just like this. And after that, we get our two-order collaboration network. When the construction of the two-order collaboration network is complicated, according to the conclusion of graph representation algorithm, such as graph attention network, the characteristic of the neighbor nodes has a positive effect on improving the representation quality of graph nodes. As shown in the picture, we define the node that currently needs representation calculation as central node. For example, the user A node, and we define the nodes connected directly with the central node, as the central nodes is neighbor nodes, such as the node user B and node user C. And then the central node will calculate the attention weight with its neighbor nodes and itself respectively. The attention weight calculation process is shown in the figure. And first of all, we define the vector of user I as this, and the H subscribe I is a primary vector of users. And then we calculate the attention weight between user I and its neighbors through this equation. In this equation, the W is a shared score matrix. And finally, we adopt a softmax function to normalize the weights, just like this equation, and in which the unsubscribed I is a set including user I's neighbors and itself. And then this formula will update the primary vector of users. The vector of the central user node is affected to different degrees by the vector of its neighborhood user nodes, and it alleviates the problem of sparse information caused by the lack of history documents. Based on that, multi-age attention mechanism is used to enhance the model's performance. As we can see from the picture, we can use several parallel attention networks to optimize primary vector of user respectively. After that, we gather and concatenate the results as a final user vector. When we do best answer recommendation, first of all, we should use the LDM model and the transformation matrix W to convert question document to the question vector and perform a dot operation between question vector and each user vector, and then predict who is the best answer according to the result of dot operation. Since there are many parameters needs to be optimized in the graph attention network, we use cross entropy function to calculate the model loss for model parameter training. Finally, we use pattern-related questions in Stack Overflow as our experiment data. The information for our dataset is in the table. For an example question in the training set or test set, the true label of it is the ID of user who provide the accepted answer for it. And we use accuracy 8n as our evaluation metric. As we can see from the equation of accuracy 8n, we considered the n users recommended by the model who are most likely to be the best answers. If there is a real best answer among them, 1 point is added to the total score. After predicting the best answers for all questions in the test set, divided the total score by the number of test samples. After that, we get the results of the experiments. As we can see from the table, our approach can achieve an effect that if exceeds the other baseline methods after tuning parameters for every approach models. And as we can see from this model, without graph attention network optimizing user vector based on the collaboration network, the accuracy drops a lot. It proves that using collaboration information has a positive effect on improving the quality of user profiling. And this is the conclusion and the future work. We proposed a document and a collaboration information-based answer recommendation method, which is effective at a level. And in the future work, we can try to build a denser collaborative network across different communities. And that's all. Thank you for your time.
Okay, Yuexin, are you here?
Yeah, I'm here.
Okay, I have a quick question for you. And I think how to. Okay. According to your approach, I want to know what are the benefits from the graph attention network for your approach design, and why you choose graph attention networks when you design your approach and for the specific task.
As we can see from the experiment, if we just only use the LDA model result as the user's profile, the recommendation performance is just not very good. And that's maybe because of some users in the community are not very active, and they have little relative document, just a history document mentioned in the slides, and that will cause the low performance of the method, the profiling method, only based on the document, and the interaction between users may show us some relative just like knowledge transform between users.
Okay.
And that will improve the performance of the method only based on the document.
Okay. So you mean GAT can help you to capture more useful information, right?
Yeah.
Okay. Thanks. Any other questions for the speaker? Okay. If no more questions, we can move to the next presentation. Thanks again.
Okay.
Okay, the last presentation is lightweight map enhanced 3D object detection and tracking for autonomous driving. And the speaker is Lei Gong from University of Science and Technology of China. And also I need to play the video first.
Hello everyone, this is Lei Gong. I'm very glad to be here to present our work on lightweight map enhanced 3D object detection and tracking for autonomous driving. This is a joint work with Shunhong Wang, Yu Zhang, etc. This is the outline of my talk. Now let me introduce the background and the motivation first. 3D multi-object tracking is an essential component for many applications, such as autonomous driving and assistive robotics. A standard deep learning-based 3D tracking by detection pipeline is as follows. Firstly, neural network-based 3D object detection model receives the point cloud data from vehicle sensors and outputs the detection results, often represented by 3D bounding boxes. The data association module will associate corresponding detection results in different frames and give the same label to the same object. Although there are many works that have achieved superior performance in real-world driving scenarios, the current tracking paradigm still has limitations. For example, the vehicle sensor performance has a great influence on autonomous vehicle perception accuracy. However, as the most important two sensors on autonomous vehicle, camera cannot provide accurate range information. The LiDAR's resolution still cannot meet requirements in some situations. As a result, in some cases, a car or person may be represented by only several points of pixels that make it hard to be detected. What's more, many deep neural network models only consider two modality data formats, the point cloud from LiDAR and image from camera. These models may only learn the data patterns and the representation, as well as the distribution bias of the data set, but still cannot understand the driving scene well. In summary, the trained offline model and the single vehicle intelligence, as well as the vehicle sensors it depends on, has limitations and makes it hard to handle the scenario change situations and corner cases. So if there are scenarios that the single vehicle intelligence cannot deal with, how about we use the additional information as external supplement? The question is, what kind of information can be used? Based on the famous idea of 5 levels of vehicle capabilities defined by the Society Automotive Engineers, the Informatics project also proposed 5 levels of infrastructure support for automated driving, which is also known as the ISA levels. In each level, they define what kind of information provided to the intelligent vehicles, like the digital map, dynamic digital information, real-time traffic situation, and even the lane advice. We call all of them same information in our paper. The idea of a combination of a single vehicle intelligence and external same information is what we know as the intelligent collaboration of vehicle to road. We observe that most existing tracking frameworks have not considered using the additional same information, even though a few open driving datasets have started to include the map data. So we raised our research question, whether additional information, such as the map information, can help to improve the performance of the original tracking framework. Our main goal is to design a universal method to use map information in various tracking frameworks. This method can be applied in many existing detection and tracking systems and decoupled with specific map formats and driving platforms. Besides, it should be a lightweight design. Lightweight means only a few modifications of a original framework are required. Pluggable means this method have lower coupling with the original tracking framework and driving platform. Real-time requires that only mild increase or no increase in latency is allowed. And most importantly, it can support more scene information in the future. Based on our research questions, we explore the utilization of mapping information in the original tracking system. Specifically, in this paper, we proposed a semantic geometric model to represent the conscious information that can be extracted from different format map data. We designed a general algorithm based on the conscious information model to improve the detection performance. This algorithm can be used both before or after the detection process. We present the method to integrate the map information and use our algorithm in various existing tracking by detection frameworks. According to our design goals, we first consider the overall structural design. As two prime open source autonomous driving platforms, Internetware and Baidu Apollo adopts designs closely coupled with the specific map format. For example, the Lanet 2 for Internetware and OpenDrive for Baidu Apollo. Suppose now we are going to use map information in M tracking frameworks. If we design N method towards N driving platforms for each tracking framework, we must design N times M method, which is too labored and does not fit our design goals. So finally, we determined to build a conscious information model that defines only necessary information. It only needs to implement interface to extract information from a different format map. Based on that model, we can design a universal method to use the conscious information in different tracking frameworks. In that way, we only need to design one method and implement in interfaces for same information extraction. For designing a universal method adaptable to different tracking frameworks, we choose to design it towards the tracking by detection paradigm. Although there are different categories of tracking methods, most recent works still focus on the standard tracking by detection pipeline. Also, 3D MOT systems following the tracking by detection paradigm have a similar framework. The tracking by detection paradigm has two most important features. Firstly, the detection and the tracking process are decoupled. Secondly, the tracking loop can also be divided into several submodules by function. Therefore, we can easily add processing to improve the accuracy using map information in these submodules. Now let me introduce our method. We propose a semantic geometric model which defines the mapping between the conscious map information and the corresponding data format. The semantic label class L contains labels, for example, no driving zones and curve lengths. The geometric value set class V is labeled sum type, contains the corresponding geometric definitions. Each component of the sum type represents a specific geometric value type corresponding to a semantic label. For example, we define the label no driving zone to represent the areas that a car cannot drive on. The value type of no driving zone is a power set of the polygon set. Each component in this set is a fitness sequence of the point, including a no driving polygon, and each point represents the coordinates of the case point. This model allows us to design the algorithm and framework based on a uniform format information, so that we don't need to modify our algorithm when implementing in different platforms. Based on that model, we can design different algorithms to use map information. In this paper, we proposed a very simple filter algorithm based on the no driving zones. We define a rectangular array ahead of the ego vehicle as a region of interest, and then we take the intersections of ROI and the no driving zones polygons in global coordinates. Then the intersections are transformed into the local coordinate system of the ego vehicle and used by the pre-filter algorithm to filter the point cloud or the post-filter algorithm to filter the bounding boxes. This is the design of our mapping enhanced tracking framework. Conscious scene information can be extracted offline and stored on the roadside. The same information will be provided to the vehicle as the external support. Enhancer is a core component designed to integrate the same information into autonomous system. The algorithm to use map information will be implemented in the enhancer. In this paper, our filter algorithm is integrated into the enhancer and provided as an application interface, which can be called directly in the original tracking systems. We made our preliminary experiment on the typical driving scenario in Qt dataset. The map data is extracted from OpenStreetMap based on the GPS data in dataset. We test the combination of one of the state-of-the-art 3D tracking map detection framework, AB3D MOT, and the 3D object detection models with walks-based, point-based, and a combination of both two paradigms. Here we show the experimental results. The precision results are shown in these tables. The left table shows the best results of MOTA, as well as the corresponding parameters of different frameworks evaluated by the 3D MOT evaluation tool proposed by AB3D MOT. We evaluated different original tracking and detection frameworks, and the frameworks integrated with the map information. From the result, we can see that the utilization of a map information can achieve a better result than the original. We also noticed that the MOTA may decrease in some cases. For example, the result of a PVRCN with a pre-filter algorithm. The main reason is that the evaluation tool proposed by the AB3D MOT would automatically try different thresholds of object scores to find the best final result. A higher threshold may ignore some true positives having lower scores. So in order to eliminate the impact of threshold changes, we use the official Qt2D MOT evaluation tool with no filter threshold. The right table shows the results. We can see that the FP number of a framework using filter method has a significant decrease, bringing the increase of MOTA metrics. As for time consumption, we can observe that the tracking system using pre-filter algorithm has a lower model inference time. And both the utilization of a pre-filter and a post-filter algorithm lead to a lower tracking time. The total time has a mild increase in latency, and sometimes the tracking framework using the pre-filter algorithm even have a lower total runtime than the original framework. Briefly then, I'd like to summarize the major points I have presented. In this work, we propose a semantic geometric model which only defines conscious information we need in tracking framework. Based on this model, we present tracking by detection framework using scene information. We design a filter algorithm using no driving zones, and the experiment shows that with map information, the tracking framework can achieve better performance. The work in this paper is a part of our design theme model, which we are now working on. Based on the multimodality data and the low-level semantic data, as well as the designed meta model, we are going to build a special temporal scene model to improve the perception accuracy and the scene understanding of autonomous vehicle in the future. Thanks. Any questions?
Okay, thanks for the talk. Lei Gong, are you online?
Yeah, I'm here.
Okay. Any questions for the speaker? Okay. I have a question for you. Owing to the additional information, I think your approach achieved a better results in the specific task. And but I noticed that the precision is around 70% to 80%. What I want to know, what are the bottlenecks for this specific task to further improve the precision?
I'm sorry, I didn't catch that. Would you please repeat this question?
I noticed that the precision is around 70% to 80%, right?
Oh, yeah.
Okay. What are the bottlenecks for this to further improve the precision?
Oh. You mean other method to improve the accuracy?
I mean the key points to further improve the precision.
You mean the key point in our method, or?
I think it is a general question for the specific task. Okay, you can talk about more about your own method, I think.
Oh, okay. This method, in fact, was inspired by the current tracking by detection tracking by detection frameworks that they didn't use the additional informations, but through the experiments we realized that in fact the additional information like the map is very important to the vehicle autonomous vehicles, because for a single vehicle intelligence there are always some corner cases cannot handle this some situations. So our idea is very simple, but we design a universal method or framework to integrate the map information into a different. So in this paper, again, so we integrated in four kinds of frameworks, and we all get a better performance than the original framework. So this is just a preliminary experiment, and now in fact we are now use more information like the curve length or the interaction between the bigger vehicle and other vehicles or car or pedestrians to make the single vehicle more intelligent to handle the corner cases of this to make it a better autonomous vehicle.
Okay, thanks for your answer, and looking forward for the new results from you.
Yeah. Okay. Thank you.
Okay. Are there any questions for the speaker? Okay, thanks again. If no more questions. Okay, I think this all for this system session, and thanks again for your attending. And we have 10 break, and welcome to back attend the next short paper session. Okay, thanks again. Bye-bye.
Hello, everybody. Kang Jie, can you hear me, Kang Jie? There's nobody here, huh?
No, Central is here. I can hear you.
Okay, okay. So I would like to check whether Bo Gao is the first present speaker of the next session here or not.
Hello, sorry, some late.
It is okay. You are here, Gao Bo, right?
Yeah, I'm Gao Bo.
Hi, wonderful. Okay, so, so Jia Wang is here already. So I think should be Marcia is already here, right?
Can you hear me clearly?
Yes. So, okay. I think all the speakers in this session are here. So let's start. Okay. First, I think welcome everyone to the session last session of today for the short paper session. So we have 3 papers to present today. The first paper will be the towards more secure and efficiency smart contract. And the speaker is Gobo from Singapore University of Technology and Design, Singapore. Okay, here's yours. Go ahead for the presentation. Okay. And one thing is that 8 minutes for presentation and 2 minutes for questions.
Wait. Can you see my screen this moment? I don't know how to.
Not yet. You can click the button, share screen.
Which I didn't find the button. Wait. Sorry, seemingly some problem with my software.
So what's the problem?
I can't find the main screen of the.
There's a button at the bottom of the share screen.
Yeah, I didn't find the button. I think maybe. Can you arrange the sequence to allow the second speaker to talk first? And
Okay.
Yeah, I think I have to quit the app and then.
Sure. Okay, let's change the order.
Okay, sorry, very sorry for
let me check with our second speaker is Wang Jiawen, is right? Jiawen here or not? Can you hear me?
I can hear you. I'm here.
Okay, thank you. Because Gao Boy is some problem with the room usage. So can you change the order to present first?
Okay.
Okay. So you can go talk now. I think first you can share a screen, then give a talk. So we already have 4 minutes of class.
It seems that the advanced option in the share screen are clogged. Can you open it?
Advanced sharing. Okay, maybe we need some technical issue. So Kang Jie is here. Can you hear me, Kang Jie? Kang Jie. So the speaker has a problem to share screen.
No. On the share screen, I have give you the co-host.
I think the speaker needs to share a screen. He wants to do the presentation. So can you give the permission to the speaker to share a screen?
There is an advanced option in the share screen. Can you open it?
So now I have give you your host.
So okay.
You
okay.
cannot share your screen.
Jiawan should be able to share screen now. Is it working, Jiawan? Can you share your screen now?
No.
No?
Yes, there is an advanced option in the share screen. It seems the manager closed it.
You just don't need to click the share advanced share screen. Just click the button share screen.
Okay, I will try.
Is there some problem? Mine problem or not? You cannot modify the one share screen as it is locked by you. So I don't have permission. So you still have problem, cannot share, or you don't know the button, where the button?
I know the button, but I can't open it.
What? Can you help? I need your help. So I think Jiawan, you already the host. I think you have the right to share your screen, right?
Yes.
What should I do? Something I don't know. Whether I think okay. Finally, yeah, you got it. Great.
So you can see my screen. Can you see my screen?
Please go ahead. Yes, everything goes well now. Maybe we go. Yeah. It'll be late.
Hello everyone. This is my report, Path-Oriented Falsification of Non-Deterministic CPS. I'm Jiawan Wang from Nanjing University. CPS are widely applied in many safety critical areas, such as aerospace control and autonomous systems. It's important to keep them working safely. However, due to their behavior's high complexity, verification is tough for them. Recent studies have proposed the falsification as a complementary approach. Instead of providing rigorous proof, falsification attempts to seek a witness behavior that violates some given safety properties in the system. Most real-world CPS are nonlinear, non-deterministic, and combine both discrete and continuous dynamics. To formalize their dynamics, hybrid automata is naturally used. A hybrid automaton is defined as the 8 tuple in HA here. We give an example HA in figure 1, where X and Y are system variables, and mu1 and mu2 are external inputs. And the 6 circles from V0 to V5 are system locations. In each location, there are flow conditions and invariant conditions, denoting the gradient and constraints of system variables. Discrete transitions of the system are denoted by edges between locations, with their reset action written above the edge, and the guard conditions below the edge. The example HA starts from location V0 and has unsafe states in location V3. During the falsification of it, we attempt to seek a control instance, denoted as delta here, so that the system will evolve to an unsafe state under delta. The 4-tuple definition of delta consists of initial values X for system variables, initial values mu for external inputs. The evolving path rho consists of locations and the dwelling time tau in each location along the path. The falsification of hybrid automata is conducted mainly in the following 4 directions.
Motion planning-based methods explore space by RTs. They grow RTs forward or backward by time. Although RT algorithms are successful in many areas, they show limited performance in HA falsification. Optimization-based methods apply heuristic global search to explore space. Bridge and Stereo are two mature falsification tools with multiple heuristic optimization methods provided insight. These optimization-based methods are designed only for deterministic hybrid automata. There is also a gradient-based method called multiple shooting. It has been combined with symbolic reachability analysis to improve efficiency. However, to achieve gradient information and the reachability analysis, they only support limited HA. Recently, a reinforcement learning-based falsification method has also been proposed. In this work, we propose a path-oriented derivative-free approach for the falsification of hybrid automata. In our framework, we generate candidate paths in the bottom layer by DFS or set. For each candidate path, we seek witness system behavior along it in the top layer. For the example HA, from its initial location V0 to its unsafe location V3, we can generate 3 candidate paths. To find a witness control instance delta, along the candidate path row 0, we encode all constraints that should be satisfied into C delta. C delta includes discrete ones, such as guard conditions, and continuous ones, such as environment conditions. We can see that C delta is often nonlinear, complex, and cannot be solved by existing SMT solvers. We then define the satisfactory degree for C delta. The satisfactory degree is non-negative, and a smaller one implies better satisfaction of C delta. It would be 0 if and only if C delta is satisfied. Thus, the satisfiability of C delta is transformed into the minimization of DC delta. To solve this optimization problem, we propose a classification model-based derivative-free algorithm. Our DFO algorithm performs cycles of classification, model refinement, and sampling. In each cycle, based on the objective function, we classify samples into positive and negative ones. Based on these newly classified samples, we refine our classification model accordingly. Then we generate new samples from the refined model and begin the classification in the next cycle. Now we apply our approach to the running example. We generate candidate path row 0 first, encode its feasibility constraints into C delta, and solve the minimization of DC delta by our DFO algorithm. It returns a minimal value of 1.105, larger than 0. Thus, no witness behavior along row 0 is found. Then we generate path row 1 and found no witness as well. Finally, we generate path row 2 and find an optimal control instance, under which the dissatisfactory degree is 0. With this witness control instance, we complete the falsification. We also provide 2 pruning techniques to improve efficiency. They prune the continuous space of dwelling time in locations and the discrete space by backtracking during the generation of candidate paths. We skip the details today due to time limitations. In our experiment, we evaluated our tool PDF and its pruning techniques and compared it with other falsification tools. PDF was tested over 28 widely used benchmarks for HA falsification, including deterministic ones and non-deterministic ones. We evaluated the success rates, simulation, iteration usage, and the time usage of PDF on these benchmarks. PDF was run without and with pruning techniques in the basic version and the optimized version. We can see that PDF generated witness example for all the 28 cases successfully, and in 24 of them has a success rate higher than 88%. For most cases, PDF generated a witness example in seconds, and it used more than 20 seconds only in the last one case. Now we compare the basic version of PDF with its optimized version to evaluate the effectiveness of its pruning techniques. Without pruning, the success rates of PDF were less than 10% in 12 cases. Equipped with pruning techniques, the success rates were enhanced to higher than 88% in 24 cases. While the success rates were improved in all cases, both the iteration usage and the time usage were generally maintained or even reduced in many cases. Now we compare PDF with Estereal and Bridge, two state-of-art falsification tools of HA. Since Estereal and Bridge only focus on deterministic HA, we compare PDF with them in the 18 deterministic cases. Bridge is equipped with its default optimization method, NM, and Estereal is equipped with 3 optimization methods, SA, SOR, and CE, provided inside. Thus, including PDF, there were 5 settings altogether. For success rates, PDF was top 1 in 17 of the 18 cases. For the iteration usage, PDF was top 3 in the 17 of the 18 cases. And for the time usage, PDF was top 1 in 15 of the 18 cases. To summarize, we propose the path-oriented approach for the falsification of the general non-deterministic CPS. And our tool, PDF, supported the falsification of a set of benchmarks effectively and efficiently. Thank you for listening, and I hope you enjoyed it.
Yes, thank you. Thank you for the talk. Any questions from the audience? Oh, seems that no questions. But also I would like to ask something, but I think I didn't catch up the main idea. Maybe I can talk to you later because we have a quite tight time. Okay, thank you, Jiawan.
Okay, thank you.
Okay, is Scope ready?
Yes, I'm here.
Okay, so let's go to the second presentation. Paper is, the title is Towards More Secret and Efficiency Smart Contract. Okay, here's yours, Bobo. Hope you can share your screen now.
I need Jiawan give back me the host.
Kangjie can help to move the host to Gaobo.
No, I just want Jiawan give back to me the host, and I can make the co-host. Hi, Jiawan, can you hear me?
Might be. Or maybe I'm not familiar how to use it. Jiawan still here? Oh, where's okay. Oh, okay, here's Jiawan is host.
Yeah, maybe he's using Linux, so I have to give him host. He can share his screen.
Oh, yes.
Okay. How can I do? What can I do? As co-host, would I have any kind of permission or privilege I can shift host?
Hi, Jiawan, is you still here?
Yes, I'm here.
Yeah, just click on my name and make me host again. Thank you.
I have ended the
So you also don't know how to transfer host to Gaobo?
Yeah, to me it's okay.
Can I
just click on
terminate it and enter it again? Or give it to you?
So how to use it? Here.
Yeah, okay.
Oh.
So are you ready, Gobo? Can you share your screen now?
Yeah, I think host disabled participant.
Oh, now Kanji is the host.
Yeah.
Yeah.
Cowboy is co-host. I think he can share his screen now.
Oh, I can't. It says host disabled participant screen sharing.
Okay, Cowboy, give you host and give it back to me after you finish your presentation. Okay.
So you, oh, okay, I saw it. Wait. Hello, can you see my screen?
Yes, go ahead.
Okay. Hello, everyone. Lastly, it's my great pleasure to give this presentation. My topic for today is towards more secure and efficient smart contracts. Here is a brief introduction about blockchain and smart contracts, but I will not give much time on it except the conclusion here. The contracts should be thoroughly analyzed before deployment. That's why I start this work. The roadmap for the analysis is like this. First, we try to test the smart contracts with the hyper symbolic execution. Then we combine the techniques of lazy annotation and loop invariant learning to verify smart contracts, and further to optimize the Gantt of the smart contracts with the verification assistant. Also, there are lots of other work planned for more secure and efficient smart contracts. I will explain these works through examples. The first one is testing smart contracts. We know that symbolic execution works by exploring multiple paths with symbolic values. Test cases are generated which lead to the problematic assertions. A key challenge is scalability, particularly related to constraint solving and path exclusion. Back to this example, the notorious DO attack, which allowed the attacker to withdraw all the money by the function withdraw here. In particular, the statement at line 25. To prevent such vulnerabilities, we define several properties concerned by users in our tool, like respect the limit, avoid non-existing addresses, be no blanco, and godless suicide extra. Then construct the control flow graph of the contract and concentrate on the money-related parts to avoid the time-consuming solving and path exclusion. With the help of SMT solver, we will return the users whether certain properties are violated or not. Here is the evaluation. It is conducted on 36,000 contracts, and we mainly concentrate on the efficiency and the usefulness of our tool. The execution time demonstrates efficiency of S compiler, and the energy time for a contract dropped to 5 seconds from 20 seconds. At the same time, we also have a remarkable performance. We newly discovered 224 unknown vulnerabilities among these contracts. So the first part is to test the contracts against predefined properties from already known attacks. What if the users want to know whether some properties hold at some place? That is the target of our second work. We try to allow the programmers to insert any property they are interested in and verify the contracts against these properties. Still this example, the post condition at line 10 says that there is only amount is allowed to be transferred out to the message sender. If there is a loop formed in this contract, that means multiple times the amount is sent to the message sender. A counterexample which violates the post condition will be returned. So this way, we can either verify the contract or falsify the contract against the sessions. If we correct the contract with global safeguards, here logged equals false at the very beginning, with the event at this moment, the event of node N5 will be logged equals true and the balance equals old balance minus amount. With this invariant, the node assertion will be implied successfully. That means the assertion will be maintained at this situation. We implemented our approach on a tool named sVerify and evaluates on multiple contracts. Our concentration mainly focuses on two common vulnerabilities, which are overflow and reentrancy. Results demonstrate that sVerify can successfully verify or falsify test cases with high accuracy. We also collected several representative contracts to insert assertions, considering overflow and reentrancy. Lastly, we discovered two new vulnerable contracts among these 7 contracts. Last work is optimization of smart contracts. The target of this work is to reduce gas consumption without damaging the security of smart contracts. And shown in this example, there are 4 kinds of cases identified for optimization. The first one is double check by users with modifier and requirement in function withdraw for user. These 2 checks are duplicates, obviously. The second one is introduced by compiler solidity, inserts checks to avoid zero divisor by default.
1 minute left.
Oh, no problem. Which overlaps with required statement here. The third one is a constant check, which we can see the ECV is constant. There is no need to introduce a safe math library at all. Last one is a redundant check in some cases, like the statement in multiplication, which cannot be validated for this statement. So we can fork the branch to jump this check directly. After analysis, the original code will be reduced from the left to the right directly. Another example is a redundant branch in a loop. We can see from source code, the right rectangle will not be reached because the statement at line 4 requires the counter should be turned. So we can infer an environment of counter larger or equal than 10 with the branch condition and assertions for this loop. With this environment, we can securely remove the code in the right rectangle. And the CFG shows these nodes are all removed after optimization. To conclude, we leverage the symbolic execution and the lazy annotation with automatic loop invariant learning techniques to thoroughly test and verify the smart contracts. We developed tools sCompare and sVerify to evaluate amounts of smart contracts. And we further develop techniques to optimize the smart contracts to reduce the gas consumption in the premise security. That's all. Thank you.
Oh, okay, thank you for your talk. I think we don't have time for the question. Okay, thanks again for your talk. Okay, let's move on. And third talk. Oh, we already ran out of time, but I think because of a technical issue, we have give more time, I think. Okay, thank you.
So I need Gabo.
Okay, make a host, right?
Yeah, thank you.
Yes, okay. I think the third talk will be with the video. So let me share the video. Can you show me and tell me how to share a video? Just let's share screen or play the video.
Yeah, you just share screen and click the open videos.
Okay, I got it. Let me open the video first. Sorry for the 1 minute. Oh, I'm not. Sorry for the time. I will share the screen with basic. No. Well, how can I share the desktop?
Yeah, I can see your screen now. And you can
It's a screen.
Yeah.
Okay. I think this one, right? Oh, sorry. Can you hear this video?
So you cannot open the video?
You cannot see the video?
No. So you need to share the video only. Do not share the Explorer. Yeah, you need to close this share screen. The share screen again and select the video.
Share screen, select the video. Now it's okay?
No. I just see your File Explorer and didn't see the video you played.
Oh, you cannot see the video. Oh, sorry. Sorry, another time. How can I share this video? So I stop sharing screen, then I click share screen. Then what I should do? What should I do? So I click the desktop, right? My gosh. Shit. So you cannot see my screen, the video you cannot see?
Yeah, I can see the screen, but I cannot see your video player.
But you're already playing.
So did you share screen and select the video player?
Yes.
Oh, that's weird. So can you give the host to 3D at this way?
Yeah, yes, that'd be better. Sorry for my not familiar with room. 3D is here.
Okay, I will share the video. Okay.
Okay, thank you, thank you. Sorry for my my not familiar with room.
You know, I can't see the video. But there is no sound. Sorry, when you share your screen, you should make sure that you click the share your voice also.
Okay, can you give the host to me and I will share the video.
Marcy, you are the co-host. I think you're able to share the screen, right? Are you able to share a screen?
I think you should give your host to D3. Yeah, not share ma. Okay.
Okay.
Okay, thank you.
So Marcia, you cannot share screen.
No, you are the host now, so you need to right click on D3 and make him host.
Okay. How can I do that?
Click his name and select more.
Okay.
Host.
Share as yes, make host. I got it. Thank you. Yes. Marcia, now you're the host.
Sorry.
Yes, sorry, because I'm not familiar with Zoom. This is my first time hosting a session using Zoom. That's really unfortunate. We are out of time, but it should be okay. So I think, Masha, you already host, right?
You gave the wrong person. You need to give it to this way. I think Marcia is not here now.
Okay, I should give you a host.
No, you have no right to operate this. I'm not sure it's
Yeah,
Marcia.
can you hear me? Masha? Oh. So what's the problem? Why I cannot share a video? Also disable touch screen share. Okay. Or not 2D is the host.
Okay. No, can you see my screen?
Yes, yes.
Thank you, everyone.
Can you hear the voice?
Yes.
Okay, let's begin.
My name is Ma Xue from Xi'an Jiaotong University. I am very pleased to be here to share our work. The topic of my paper is investigating the impact of issue links on bug localization. This is an empirical study, and the outline of my work as follows. The first part is introduction. We know that bug reports are continuously emerge, and one of the most time-consuming tasks to resolve a bug report is to find the buggy files. Researchers find that most bugs reside in one or two source code files. To address this challenge, bug localization techniques are proposed to identify buggy files, and information retrieval-based bug localization has received a lot of attention due to its low computing cost and minimal external dependencies, and they work by computing similarities between a reported bug and source code files. And now, 6 state-of-the-art IRBL techniques are widely welcomed: Bug Locator, BLUIR, BR Tracer, AMALGAM, and BLIA and Lucas. But most of these IRBL methods treat each bug report individually or independently. And in practice, some bugs may be dependent with each other. Relations between bug reports called issue links, which developers referred, and in practice, bugs associated with issue links may be patched on similar code locations. So, in this letter, we test that if this correlation can further be leveraged as clues to improve the accuracy of locating bugs. The second part suggests preliminaries and example about bug reports. A bug report is a document submitted to describe an error, and it contains a number of fields. We are particularly interested on 3 of them, namely issue number, description and patch, and issue links. This figure shows a bug report from Jira, which is a big issue tracking system, and the issue number provides a reference number that can be used to identify commits in version control systems that fix it. The description and patch fields present the textual description and be used to identify bug location files. And the issue links fields are used to further extract the relation between bugs. And the third part covers the study approach of this letter. First, study design. We designed and studied the following research question. First, how do bug reports with issue links interact with each other? Second, will reported bugs with issue links be patched on similar code locations? Third, do state-of-the-art bug localization techniques produce similar recommendation results for a pair of bugs with issue links? Then, to answer these questions, we conducted an empirical study on 836 fixed bugs in project named HBase. To answer RQ1, for each reported bug, we reviewed its descriptions of bug reports and manually inspected its associations with other bugs as issue links. To answer RQ2, for a pair of bugs with issue links, we distilled the set of involved modified source files from gathered code pages as bug locations. We further calculated the similarity of bug locations to measure the impact of issue links. To answer RQ3, for a pair of bugs with issue links, we ran out top 10 prioritized bug similarity of recommended results to measure its influence on existing IRBL techniques. This figure shows the overview of study approach, and all of our data comes from Jira and Git. And the fourth part shows the results of our work. And this form is our preliminary study the results of issue links. And for the issue link classification, we manually identified 220 pairs of issue links involving 212 of 836 reported bugs. And for these extracted issue links, we further manually classified them into 4 types: depend type, content type, duplicate type, and relevant type. And for question 1, we find 4 types of issue links, including depend type, content type, duplicate type, and relevant type, which covers a significant proportion of bugs. For question 2, we calculated the similarity of bug locations to observe will reported bug with issue links be patched. And we found that bugs with issue links present at least 35% similarity on locations on average. And each type of issue links also has at least 50% similarity on bug locations. It suggests that each type of issue link should deserve our enough attention. And for question 3, we used the top 10 recommendation results and calculated its similarity to assess the performance of IRBL techniques, and find for studied 6 bug localization techniques, the average similarity of recommendation results for bugs with issue links ranges from 21% to 36%, which is significantly lower than the similarity of actual bug locations. It implies that all of the studied state-of-the-art techniques can be further improved with issue links. And we further analyzed the results of 4 types of issue links with 6 techniques, and found that existing techniques lack enough support on 3 types of issue links, including depend type, content type, and relevant type, compared with the duplicate type, and they can be further improved by leveraging various types of issue links. And finally, simple implications are given. We discussed the follow-up research motivated by our study. First, automatically extracting issue links between bug reports. Second, building taxonomy of issue links and automatic classification. And third, leveraging issue links to improve bug localization. Okay, that's all. Thank you for listening and look forward to your questions.
Okay.
Okay.
Thank you, Marcia and JD. So I think we don't have the time for the questions. We already 20 minutes over. Okay. Okay, thank you everyone. And today I think the last session. Thank you for attending this talk. Okay, thank you. Thank you, County, for help. Bye bye.